Alright, so here are the things we're going to do today. Let's see. Is this thing working? Yes. Alright, so here's the things we're doing today. I have to work from home, so I'm not using my regular pens. And also, I could only find 3 sheets of paper in my entire apartment. So, also I'm getting rid of this one, I think. And we're going through the midterms. So let's start with the midterms, just because. Alright, it's the snaky midterm. You want to do snake or cake first? Hey Bethany, snake or cake?
Snake.
Snake first. Alright, snake first. Oh, these ones already have answers in them. Is there a snake without answers in them? Alright, well, I guess I'll just read you the answers. These ones don't. Okay, well, I guess the one of the TAs was writing in this one. So we start with true or false questions. This one says, if two scientists in different inertial reference frames measure a collision. So in this one's, if it's true, I say true. If it's false, I say false, and then explain why. So if two scientists in two different inertial reference frames measure a collision, they will disagree about a lot of things. That's definitely true. But they will agree about how much the momentum of each object has changed. And that's true. We talked about that in class. The idea is that they're all going to disagree about what the momentums are. They're going to disagree about what the initial momentum of an object. So they look out and they see a truck and they're like, hey, this truck has some initial momentum. And then the truck hits a giraffe and has some final momentum. And they're going to disagree what the initial momentum and the final momentum are, but they're both going to agree about what the change in momentum is. Right? Okay, next one. Incoherent deformations and coherent deformations are both forms of potential energy. Alright, false. Incoherent deformations aren't potential energy. They're a type of internal energy, but they're not potential energy. Only coherent deformations are potential energy, just like the marker recognized. Next question. One way you can tell if you are in a non-inertial reference frame is if isolated objects are accelerating. That's definitely one way to tell if you are in a non-inertial reference frame. If objects that you, by your estimation, should feel no force, if those objects accelerate, it means you're in a non-inertial reference frame. The rule of inertia doesn't hold. Last one. When I examine a system in the zero momentum reference frame, the kinetic energy of the system is always zero. That's false. To explain why, hey look, that's my writing. To explain why, let's consider 2 examples. So this is m is equal to 1 kilogram, m is equal to 1 kilogram, v is equal to plus 2 meters per second, v is equal to minus 2 meters per second. Okay, so if this is the scene we're seeing, we're in this system zero momentum reference frame. How do we know? Well, the momentum of this is plus 2, the momentum of this is minus 2, so the total momentum of the system is plus 2 minus 2, plus 2 minus 2, 0. Zero momentum. But this thing has kinetic energy, right? So the kinetic energy of the first one and the kinetic energy of the second one, 1/2 times 1 times 2 squared plus 1/2 times 1 times minus 2 all squared, and that's equal to 4. Not 0. So sometimes if a system's in a zero momentum reference frame, it does have zero kinetic energy, but this is not one of those times. Next question. Alright, a person is standing still on the ground. I'm sorry, I'm very sleepy. It's Saturday morning. A person is standing still on the ground and watches 2 carts collide on a frictionless track, and another person rolls past in a car with velocity 2. The person in the car is named Carl. Carl. All right. The person on the ground describes the collision in the following way. One cart has mass 2 kilograms and initial velocity v, and the other cart has mass 5 kilograms and velocity vb minus 2. The two carts collide, they stick together. Oh, I'm so sleepy. Is the system isolated? Yes. Cars, it's rolling. It's fine. If the person on the ground describing what they see in an inertial reference frame. Yes. What they see is in an inertial reference frame. Good. Determine the total momentum of the system. 2 times 5 plus 5 times minus 2 is equal to 0. What's the velocities of the carts after the collision as described by a person standing still? So after, the total momentum is going to be the masses added together because they're stuck together. V final, so it's going to be 7 times Vf, and that's going to equal P total, that number, 0. Vf is equal to 0. Oh, it's because we're in the zero momentum reference frame and they stick together. Calculate the amount of thermal energy generated in the collision. Okay, well, Ke final is equal to 0. Ke initial is equal to 1/2 times 2 kilograms times 5 all squared plus 1/2 times 5 times minus 2 all squared. This is equal to 25 plus... Oh man, it's so rude to yawn all the time. But I do what I need to, which is yawn all the time. So the initial kinetic energy is 35 joules. The final kinetic energy is 0. So the change in kinetic energy is going to be 35 minus 0. Oops. Change in kinetic energy is 0 minus 35. So the kinetic energy has gone down by 35 joules. And so the thermal energy has gone up by 35 joules. Hooray. Everybody gets joules. It's like a wedding. Convert the velocities of the car's reference frame. Oh, Carl. I should have called it Carl's reference frame. Show the amount of thermal energy produced the same way. Oh, this question's tricky. Tricky. All right, so to do this question, we just need to reproduce the previous question, only in a modified reference frame. So Carl is going to see car A with a different velocity. Carl's going to see car B with a different velocity. And Carl's going to see the final velocity as being different than the person standing still. This is going to be VA minus Carl's velocity. So VA is 5 minus 2. That's 3 meters per second. VB is VB minus V Carl. So that's minus 2. Oh, Carl, what did you do? And the final velocity was 0. V final minus Carl's 2 is equal to minus 2 meters per second. Okay. So this question mirrors a question we did on the homework that a lot of people asked me questions about, where I told them to convert everything into the zero momentum reference frame before doing everything else. Essentially, this thing starts in the zero momentum reference frame, and then we're asked questions about it. So how much kinetic energy gets converted? I want the change in kinetic energy. So kinetic energy total, initial, 1/2 times 2 times 3 squared. 1/2 times 5 times minus 4 squared. Where's my calculator? I brought my calculator home with me. Alright, so this is 3 times 3 plus 5 times 4 times 2. 49 joules initially. Kinetic energy final total is equal to 1/2 times the total mass of the car, which is 5 plus 2. So this is the total mass when they're stuck together. And the final velocity is minus 2 squared. So this is 14 joules. So the initial kinetic energy and the final kinetic energy are different. And the initial kinetic energy of the cars and the final kinetic energy of the cars are different. But if all we want to do is find the thermal energy, E thermal, it's going to be minus the change in kinetic energy. So this is KE final minus KE initial. So this is 14 minus 49. 35. It's going to be 35. Just like before. This is something we talked about in class. The overall idea is that everybody's going to agree, even if nobody can agree about how much energy each car has gained or lost. Everybody's going to be able to agree on how much thermal energy is generated. Oh, the last question. Oh, this is the derivation we did in class. Two cars bump into each other on a frictionless track. The first has mass ma and is moving with velocity va. The second has mass mb with velocity 0. Show that if the collision is elastic, that the total kinetic energy of the system is the same before and after the collision. Justify each step and explain the argument. There's two derivations. There's two tacks to this derivation that you can take. So one of them is to say the momentum is conserved. And so you go, okay, so this is MAVA initial plus MBVB initial. MAVA final plus MBVB final. And the second thing is to say that, so this is conservation momentum. You also have conservation of energy. Nope, it's not conservation of energy. You have the elastic collision criteria. And the elastic collision criteria is just that the relative velocity initially is going to be equal and opposite to the relative velocity final. Okay? So the speed coming in is the same speed going out. The relative speed coming in is the same as the relative speed going out, but the directions switch. So this is V initial minus V. I'm sorry about all the yawning. Minus V A initial final plus V B final. Okay. And the result is that I have two equations. And I don't know VA and VB. Now, the way a lot of people did this on the test is the same way as we did it in the class, which wasn't, and I accepted it as a fine answer because we specify some initial conditions in this, but you don't really need to. Okay. So we'll call this A and call this B. And so what they did is they rearrange A and B in the following way. You put all the A's on one side and all the B's on the other side. So the A becomes MA VA initial minus VA final is equal to MB VB final minus VB initial. And you similarly rearrange B. This comes to this, so it's VA initial plus VA final is equal to VB final plus VB initial. And now you multiply these two together. So I'm going to multiply this thing with this thing, and I'm going to multiply this thing with this thing. And since this value is equal to this value is equal to this value, if we multiply these two together, you should get the same value as if you multiply these two together. So it's MAVAI minus VAF, VAI plus VAF. VBF minus VBI, VBF plus VBI. Okay. And now I'm going to multiply out. FOIL rule. So it's MAVAI all squared plus MAVAI VAF minus MAVAF VAI minus MA VAF all squared. And these two cancel. And similarly on the other side, it's equal to MA MB VBF all squared minus MB VBI all squared. Okay? So the left-hand side has two terms, and the right-hand side has two terms, and the middle terms cancel out. And then what we do is we rearrange again. We put all the initials on one side and the finals on the other, and then divide by 2. And you get MAVAI all squared 1/2 plus 1/2 MBVBI all squared 1/2 MB F all squared. So this is the kinetic energy initial, and this is the kinetic energy final. So in other words, starting with these two assumptions, elastic collision criteria, conservation of momentum, you can end up at this point. Boop, boop. There's another way to do it. Not really many people did it on the test, but if you want to, you can use these explicit things and just brute force the algebra. So the conservation of momentum in this case would be MAV is equal to right, and the elastic collision criterion would be the initial velocity is equal to minus VAF plus VBF. I'm copying that out from here. Yeah, because the initial velocity of I is V, the initial one of that is 0, and then so that's equal to this. And so the trick here is that we can combine these two algebraically. So yeah, algebra, everybody's old friend. MAVAF plus MB V minus VAF. Now what do? You want to look at the conservation of energy. So you go, how did I do this? Oh geez. I'm too sleepy this morning. I haven't had enough tea. How I don't know. Let's see what happens if you square it. Okay, so let's square both sides. Square both sides and divide by MA. Okay, so then this side is going to look like V squared over MA. Wait, no. Oh, geez. Like I said with the caffeine, MA V squared. That side's going to look like this. This side, who likes multiplying? Raise your hand if you like multiplying. Well, I was hoping more of you would like multiplying, but that's okay. So what we do is you go MAVAF. Oh, jeez, I don't care enough. Can I just come to my office? I'll show you how to do this longhand. It's whatever. This is the easy way. Yeah, so it was a derivation we did in class, and if you want to do it algebraically, it's a little bit more onerous, but these conditions make it algebraically simpler. That's it for that test. I'm done with snakes. It's time for cakes. Oh, jeez. I wonder if anybody's watching the feed. Nobody's watching the feed. Oh, 4 people are watching the feed. What the hell? I mean, heck. Hi, everybody. All right, well, it's time for cake. Here's the cake test. Oops, sorry. All right, true, false. Let's just power through. Maybe at the end of this I'll show you the derivations on both the cake and the snake test were the same. So maybe I'll show you the other derivation with a little bit of a running start. The other method for doing the derivation. All right, true or false? Wake up. If one inertial reference frame says that an object is sitting still, all inertial reference frames will say the object is moving with constant velocity. That's true. One thing that a lot of people keep getting caught up on is the idea that v is equal to 0. This counts as moving at a constant velocity. This is a special subset of moving with constant velocity. But the idea here is that this word, it's just, I don't know, it's not very important. And this one totally is. And part of the reason for that is that all motion is relative. So essentially what we're saying is it moving at a constant velocity or is it accelerating? And so if somebody's sitting at v is equal to 0, then his acceleration will also be 0. And if he's constant, if his acceleration is 0, then he's moving at constant velocity. Okay, let's try not to get too lawyery on this. Potential energy is another way of saying internal energy. No, that's false. People are asking me about why this is. The easiest way to do it is to talk about it in terms of a Venn diagram. So you have types of energy, right? So according to the thing we did in class, you can cut this into 2 different types. There is kinetic energy and internal energy. Okay. So of the types of internal energy, there's actually different types. Like there's thermal. That counts as one. And another one is potential energy. Okay. So the idea here is that potential energy is a type of internal energy, but all internal energy isn't necessarily potential energy. Thermal energy, you're not going to be able to get thermal energy back out of a system once you've converted your energy into thermal energy. Next question. The principle of relativity says that all inertial observers will describe a system as having the same total kinetic energy. That's false. False. It's false because, number one, they won't. Different observers are going to disagree about how much energy a system has. Depending on how fast you're moving relative to the center of mass, you might say that the energy is pretty small or the energy is huge. So they're not going to agree on how much energy how much total energy a system has. 2, the principle of relativity says that the laws of physics are the same for all observers. Same laws of physics. So if you wanted to, you could say that this particular sentence was wrong because the ending was wrong. The words were wrong. And that, I guess that works. I don't like these true and false questions. The principle of relativity will say that all inertial observers will agree about how much each system's change in momentum will have, and how much energy gets converted to thermal energy. They'll agree about that, but they're not going to agree on how much total energy there is. Sorry. Convertible kinetic energy. Well, hold on. Let me draw some convertible kinetic energy for you. Oh, the race machine just went off. All right. That's convertible kinetic energy. My wife's not in the room. I'd make her come laugh at my joke, but she's not here. Do you want to come laugh at this joke? She says she doesn't want to come and laugh at our joke. Well, fine. Convertible kinetic energy represents the energy associated with how objects of the system are moving relative to each other or the center of mass. This is actually a pretty good thing, and a lot of people, and I think I might phase out this type of question because people are a little bit confused about how to answer it. The question says, if the statement is false, explain why the statement is wrong, or provide a counterexample. And that's more or less what we've been doing. But in this one, a lot of people said this statement's false, and it is. And then when they wanted to justify why they said, convertible kinetic energy is the energy associated with how much, and then they went to how much of the total kinetic energy can disappear in a collision or something like that. Although that would be kind of right too. I think mostly it was people going to their textbooks afterwards and disagreeing with whatever. Anyway, moral of the story is, this system, one of the things I want you to pick apart about this is, oh wait, no, this statement's true. So they would say false, and they would say, this this was in the textbook, and it said that the convertible kinetic energy represents the energy blah, 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 blah. And yes, the textbook does describe convertible kinetic energy as something different. This particular statement, we actually talked about it in class. So let's suppose we have our object that's a convertible. Alright, I'm going to play the cover up with the hand game because we don't have a chalkboard ahead of us. Okay. So, let's suppose all these speeds are the same. If this, oh shoot, AC, and this one is BC. Okay. Okay. Ready for my explanation. Alright, so if this is our system, it's got a lot of kinetic energy, right? This guy's moving and this guy's moving. But it doesn't actually have any convertible kinetic energy. And one of the reasons is because, or one of the ways to describe it is, it doesn't have much convertible kinetic energy or any at all, because these two things aren't going to hit each other. If this one keeps going forward at constant velocity, this one keeps going forward at constant velocity, they're never going to hit each other. Alternatively, one way you could describe this system is there is a center of mass in the system that's moving at the same velocity along with them. So you can verbally, descriptively break down the motion in terms of motion relative to each other, right? There's a lot of kinetic energy in this, but there's none of its convertible kinetic energy because they're not going to hit each other. On the other hand, if this is our system, or this and this one, it has the same kinetic energy as it would before the first system. However, all of that well, I don't know if all of it, lots of that kinetic energy is convertible because these two things are definitely going to hit each other. So there is an element of convertible kinetic energy. Convertible kinetic energy is a descriptor that kind of helps us get a sense of how much energy can be released if and when these things collide. If they're not going to collide, then there's no convertible kinetic energy. So in this case, there is some kinetic energy convertible, and this one they're not. And the distinction between these two examples is that in one of them, they're not moving, they're moving in the same direction. There's no motion relative to one another. There's no motion relative to the center of mass. Whereas in this one, they're both moving towards the center of mass. They're both moving towards each other. And so there's going to be a lot of convertible kinetic energy. Does that make sense? Oh yeah. Next thing. Long answer. A rocket traveling through space with velocity 100 meters per second relative to the Earth had mass 100 kilograms. It blows up, converting 200 joules of source energy into kinetic energy. Here I am sitting on Earth. Here's my rocket. Wow. Okay. And then it blows up. I don't know anything about these velocities. I'm just going to draw them moving in opposite direction for whatever reason. They might not. They might be moving to the right. But that's the idea. Boom. Okay. So, this question is literally the question we did. I mean, I referred to it when we were doing the other question. It's literally the same type of questions we did from the homework. And the strategy for doing this is literally the same, which is convert to the zero momentum reference frame, analyze the system in the zero momentum reference frame, and convert back. People kind of got caught up on this one. I think they had the converting between reference frames, I think, is a little bit tricky for you guys conceptually. And I hoped it wasn't, because I was giving you assignments based on it, and we were talking a lot about it, but... well. Okay, so let's convert to the zero momentum reference frame. What's the velocity of the zero momentum reference frame relative to Earth? It's 100 meters per second. Why? The zero momentum reference frame is essentially the reference frame of the center of mass of the rocket. Okay? So if I was an observer over here traveling at 100 meters per second, I would say that center of mass is not moving. How much total kinetic energy does the rocket have before it blows up in the zero momentum reference frame? I'll call it Z. Z relative to Earth. So I want the velocity of the rocket relative to the zero momentum reference frame. So that's 100 minus 100 is equal to 0. So the rocket's not moving in the zero momentum reference frame, and kinetic energy is 0 in the zero momentum reference frame. Alright, now that's in joules. Yeah. So I expected people to get 100% on this question because it's pretty easy. Okay. How much total momentum and total kinetic energy will the two parts have after the explosion in the new reference frame? Okay. Is the system isolated? Yes. The two parts of the rocket that explode, they're isolated. They're only pushing on each other. So, the initial momentum in the zero momentum reference frame is 0 because it's the zero momentum reference frame, and that's not going to change. The final momentum in the zero momentum reference frame is 0. Alright, how much kinetic energy are they going to have? Well, some source energy was released in the explosion in this description. So KE final is going to equal 0 plus 200. 200 joules. And honestly, if you just wrote this and this, you'd gotten 100% on the question so far. You should note two things. I think a lot of people kind of got caught up. I didn't want to tell you that it was the zero momentum reference frame each and every time, because if you haven't noticed, momentum comes up a lot in these questions, and if I tell you what the momentum is, it's not a question. So in this question I'm referring to the new reference frame. That's the reference frame from this. The new reference in this reference frame, that's the reference frame from the first part. My markers tell me that people got a little bit confused with this. I can imagine that there's a lot of second guessing going on, but honestly, this is a wording thing. 0 people asked me during the exam what reference frame I was talking about. So, yeah, test taking advice. If you're in an exam and you're having trouble understanding what the sentence means, you can ask somebody. If you don't, here's how it goes. If you come up to me and say, hey, do I use conservation of energy to answer this question? I will literally say, I'm not allowed to tell you that. But if you say, what is this word referring to? I have to tell you what it is. Not just in this class, in every class. Chemistry, biology, English. If it's a wording question, always ask. If there's any uncertainty, always ask. If anybody had said this during the test, hey, we're having trouble figuring out what you're referring to in this question, I probably would have made an announcement at the start of the class that everybody would have ignored. But in any case, yeah, I think it's obvious what new reference. The first thing I do is have you change reference frames and then do all the calculations in the new reference frame. I don't know. Anyway, find the velocity after the explosion in the new reference frame. Okay, so the energy afterwards is going to be 200, so that's 1/2 ma va squared, 1/2 mb vb squared, And we know that momentum is conserved. MA, VA, MB, VB. So we can do some substitution. So you get VB is equal to minus MA over MB VA. I'm going to substitute that in for this. So this is 200 is equal to 1/2 MA these are numbers. This is a number. This is a number. Let me calculate those right now. So this is 60 kilograms divided by 2. So this is 30 VA squared. This is 40 divided by 2 times 6 divided by 4 times 6 divided by 4. 45 VA squared. So VA is equal to plus or minus 200 divided by 70. Take the square root of that. 1.7 meters per second. VB is equal to 1.7 times its mass divided by 40 minus 2.55 meters per second. Which one's going faster? This one. Alright, wait, hold on. It says part B ends up with the higher velocity of the two. So we'll call VA minus 1.7 meters per second and VB plus 2.55 meters per second. And then determine the velocities relative to Earth's reference frame. So VA Earth, all these things are VA0. There's zero momentum. Oh, you couldn't even see. Why didn't everybody say? You should have raised your hand. VA is a velocity of Earth plus VA Z. Zero velocity relative to Earth. So I'm just going to add 100 to each of these. VA is equal to 100 minus 1.7. VB is equal to 100 plus 2.55. So that's equal to I guess that's a 6. All right. Well, take a look at that. You happy? So that's how you do it. It's not rocket science. Yeah. Yeah, it's literally an assignment question. So that's good. You guys have been working hard, and I'm happy. All right, next question. All right, I promise I'd do this for you. Okay. All right. Right. So momentum. We'll call it MAV is equal to MAVA plus MBVB. This is the final velocity. And this is the final velocity B. I just don't want to write it over and over and over again. So then the kinetic energy. It's not kinetic energy. It's the elastic collision. So this is VA minus VB initial is equal to VB minus VA final. That's the criterion. So this is V is equal to VB minus VA. That's the other. Okay, so here's the thing. We've got two equations and two unknowns. We don't know VA or VB. So let's solve for them. The result will be an expression involving V's and MA's and MB's. Okay? So what's the fastest way to do this? Let me see. We can go MAV is equal to, I'll substitute this one like before. MAVA plus MB V plus VA. Yep. Okay, and now I'm going to solve for VA. So I'll move this one to this side. MAV minus MBV, and I'll have the VAs on this side. MA plus MB times VA. So VA is equal to MA minus MB over MA plus MB. Good, times V. And then that I can use this equation to figure out what VB is. VB is equal to V plus VA. So it's V plus MA minus MB for MA plus MB times V. So this is 1 plus MA minus MB. I can barely see. Hold on. Over MA plus MB times V. And that's equal to, I can add these two together. I need to make the denominator of this match this. And the result is the MB's cancel out and you get 2MA times V. Alright, so now I have an expression of MA involving V and an expression involving MV in terms of VB. So I know VA in terms of V, VB in terms of V. So let's plug these in to kinetic energy final. KEA plus KEB 1/2 MVA A squared 1/2 MBVB all squared. So this is the following is the calculation I kind of had in mind when you were doing this, because I knew we covered it in class, and when I designed the problem I couldn't remember the algebraic trick we used in class where you multiply each side. Most of you use that one, but it's also possible just to use brute force algebra, which is what we're doing right now. 1/2 MA VA squared is going to be MA. Oh, I switched up the capitals and the lowercase. I guess I'll call this little a. All squared V squared. 1/2 MB times 2MA. Okay, So you get an expression that looks like that. And now the trick is to multiply everything out. And you get 1/2. And the denominator here is MA plus MB all squared. And this is V squared. And the numerator gets zany. MA to the 3 minus 2 MA squared MB plus MA MB squared. And then there's this term plus this goes squares, so this is 4 MA squared MB. I just barely made it. Alright, so here's the lucky bit. No, there's no squared on this. I got carried away. Okay, so that this term and this term match. They partially cancel out. And the result is 1/2 MA3 plus 2 MA squared MB MA MB squared MA plus MB all squared V squared. And this becomes, you can factor out an MA term, and that becomes MA squared plus 2 MA MB plus MB squared all over MA plus MB squared V squared. And this numerator is the same as the denominator. 1/2 MA V squared, which is the kinetic energy of the system. Initially, I did it. So don't say I can't do it. I just don't like it. That's the midterms. How are we trucking along? Ooh, I gotta hurry up. I want to go. I got other things to do today. Alright, so like I said, I only have 3 pieces of paper here. So I don't want to run out of paper. 8.80. Let's go. Let's go. You push. So this is in your textbook. Open your textbook. I'll read the following. I'll read it together. You push your 0.7 kilogram pillow across your bed with a constant force of 10 newtons. The bed provides a frictional force of 6 newtons. What is the acceleration of the center of the mass of the pillow? Oh, I see. Yeah, I unwittingly chose a weird question. This is a weird question because the pillow is going to get all bunched up and weird as you push it. So the pillow might rearrange itself on the bed as you push it. But in any case, you're pushing it this way with 10 newtons, and the friction force is this way with 6 newtons. So the total force is 10 minus 6, that's 4 newtons. So the acceleration is 4 divided by the mass. Divided by 0.7. So that's 5.71 meters per second squared. Yeah, you can really rifle that pillow into your wife. Who will then say, "Why did you hit me with a pillow?" And you can say, "Well, I was doing physics." And she'll say, "Well, I'm going to leave the room while you do this video cast." No, I didn't ever rifle my wife with a pillow. I'm very nice. Okay, you're climbing a rope straight up towards the ceiling. Fun. Oh, I love this question. Okay. You're climbing a rope straight up towards the ceiling. What are the magnitudes and directions of the force you must exert on the rope in order to accelerate upwards at 1.5 meters per second squared, and assuming your inertia is 60 kilograms, if the maximum tension of the rope can support is 1.225 newtons, what's the maximum inertia the rope can support at this acceleration? If the inertia of the rope is so small, the gravitational force exerted on the rope can be ignored. In other words, we're dealing with a rope who has no mass. So it doesn't need any tension to stay up. So all of the tension, if we're essentially assuming that all of the tension in the force goes to pushing our heavy butts up the rope. The reason I like this question is it focuses on systems. Here's the rope. Here's me. Disappointing everybody with my poor... Oh, no, wait. It says I'm accelerating. Haha. Okay. So the reason this question is deliberately confusing, and it's deliberately confusing because we really want you to think about systems when you are analyzing these things. So what is the system we're talking about? It's just me. What's the environment? It's the Earth and the rope. So gravity pulls down. If I'm going up, there must be a force pushing me up. So the force from the rope must be pushing me upwards. And now you can say, no, it's not the force from the rope, it's the force from my arms. Aren't my arms the thing doing the pushing? Well, you're right and you're wrong. But consider this distinction. We're trying to draw the distinction between systems, okay? That's the element at play here. We didn't say, hey, if I have a torso and I have arms that are attached to the torso, how is my torso going into the air? We're saying my system is my whole body. So what's touching my body? It's the rope. It's friction from the rope. Friction between my hands and the rope that's pulling me upwards. Consider this. Imagine this rope is super slippery. Imagine it's covered with oil. You can't get a grip. Even with the strongest arms, if it was totally covered in oil and you couldn't get a grip, you would go down. There's no way you would accelerate upwards. It's force from the rope on your hands that's pushing you upwards. Okay, so, yeah. Rope pushes up. Me up. Words. Okay, what's the magnitude? The acceleration is plus 1.5 meters per second. So the net force is going to be the mass times the acceleration, so it's 60 times 1.5. $90 newtons. So this plus this is equal to a total of 90 newtons. mg is equal to 90. Rope is 60 times 9.81. $678.6 newtons. Any questions? All right, so part B of this question is real great. It says, suppose there's a maximum tension, okay? And by that we mean, let's suppose that if I pull the rope too hard, it will break. It's a very old rope. You pull the rope too hard. So here's the rope. Here's you pulling on the rope angrily. If the tension force in the rope is too large, the rope's going to break. So the max tension force apparently is 1225 newtons. So what? How does that enter into this question? Well, here's the idea. Equal and opposite forces, right? Your hand feels a force from the rope pushing up. And that means that the rope will feel a force from your hand pushing down. Okay? So the force from your hand pushing down is equal to the force pulling up. So, in other words, what we're trying to say is that this term here, the force from the rope, that has a maximum value. So, what would that maximum value be? A times m is equal to Fg plus F rope. So this is 1.5 times the mass is equal to minus 9.81 times the mass plus the maximum force, 1225 newtons. So the issue here is there a mass that exceeds this tension force? The answer is certainly. You can rearrange this equation, 1.5 times m plus 9.81 times m, 1225. So m is equal to 1225 divided by, yeah, it's my sweet calculator. I found it. It was in my bag. 0.5 plus 81, boop, 108.4 kilograms. So if you have a mass of 108.4 kilograms, you don't have to climb the rope in gym class because you will break the rope and then you will be the most popular person in school because everybody hates climbing the rope. I don't know. I didn't actually have to climb a rope in gym class. It's something I always did on television. Do they do it anymore? If you ever had to climb the rope in gym class, feel free to tell me because I'm incredulous that anybody had to do that. Right? It seems like a safety thing. The kid would climb up the rope and then fall and then, die, and then they'd sue the school. So, I don't know. When a 5-kilogram box is hung from a spring, the string... Oh, it's a spring question. I love spring questions. Hung from a spring, the spring stretches to 50 millimeters beyond its relaxed length. In an elevator accelerating upwards, how far does the spring... Oh, I love this question. This question is fantastic. I'm going to put this question on the final. I don't know if I am. If I could remember, I totally would. Okay. So what's the idea here? The idea here is that springs, the amount of force a spring pushes up depends on how far it's moved from its resting position. Okay? So, so here's the idea. Spring force satisfies Hooke's law, named after the captain. Okay? So in this case, this number is 2 millimeters. Okay? So the spring descends, and it needs to descend a certain distance before the stretching force can match force of gravity. So that's the first part of the question, and it's an interesting clue. Because if we're then in an elevator, x equals 0. If we're then in an elevator, and the elevator is accelerating upwards at 2 meters per second, in this case, all the forces balanced out. Now, when it's going upwards, the spring force has to be stronger than gravity, right? The spring needs to pull upwards on the box much harder than it did in the first case in order to get this much upwards acceleration. So, how far does the spring stretch? What's that value? Let's think about it like this. We've got x. Acceleration times mass is going to be equal to, okay, so there's two forces. There's the spring force, and there's spring, and there's gravity. Okay? So spring force plus gravity. So spring force is minus kx. X is going to be a negative number because we're below the rest height. Plus, nope, minus mg. Okay. How do we answer this question? Well, here's the idea. The idea is that I don't know a bunch of things. I know what this number is, and I know what this number is. I don't know what that number is. I don't know what that number is. I don't know what this number is, and I don't know what this number is. Oh no, what am I going to do? The deal is that I can use this information to figure out some of the missing details of this. Because I know it's in equilibrium. 0 acceleration. Oh, come on. If A is equal to 0, that means the forces cancel out. Okay? And that means that K right now is in, I'm going to write it in newtons per millimeter, just because they're giving us all the numbers in millimeters. Okay, so M times 9.81 is equal to 20 times K. So here's the idea. I don't know what M is or what K is. If I knew what one of them was, I could use this expression to figure out what the other one was. But I don't know either. And in this case, still don't know either. But, I can replace for K. K is equal to 9.81 divided by 20 times M. You can replace that up in this thing. So it's plus 2 times M is equal to minus 9.81 over 20 times M times X minus 9.81 times M. Now all these M's are going to cancel out. Cancel. And so the result is going to be 2 plus 9.81 times 20 divided by 9.81 ta-da! You try that one yourself. Pretty fun. How much more time do I have? Got a little bit more time. Not much. I will do, I guess, one more. 8.65, which one's that? Oh yeah, you guys need to see one like this. 8.65 goes like this. A 1500 kilogram car goes from V initial is equal to 0, V final is equal to 100 kilometers per hour, delta t is equal to 60 seconds. It wants the impulse and the average force. Before we do that, we need to convert this guy into meters per second. So it's 100. Show them the long way. 100 kilometers per hour. So there is, I want the top one to be in meters, and there's 1,000 meters per kilometer. These two can cancel. And I want the bottom one to be in seconds. And there's 3600 seconds in an hour. Cancel, cancel. So that's 100 times 1,000 divided by 3600. 27.8 meters per second. Okay. So, P initial, that's 0, yeah, 0 velocity. P final is mv final, so it's 27.8 times 1500, 41700 kilogram meters per second. So its change in momentum is going to be 41700. And B force is just delta P over delta T. So it's 41700 divided by 60. .695 newtons. You can take that to the bank. Next question. All right, let's see what else I have time for. Oh yeah. This question's easy. 8.89. Crumple zones. This is actually the way a lot of helmets work too. It's a pretty fun idea, and once it's been explained to you and you can look out for it, you will see this explanation literally everywhere. Whoa! Somebody wrote something on the wall. What'd they say? There was a climbing rope at my elementary school, but we hated it. Wow! But did you have to climb it? That's the question. Did you have to climb it? I never had to climb anything. Not once in my life. That's why my feet are flat. Okay, that's not true. Don't think that's true. It's genetic. Okay, crumple zones. Okay, so here's the idea. Here's your car. And you're moving with some velocity. And then there is a wall in front of you. Okay? Now, you and your car have mass. I guess, let's say you have some mass. Okay? So you have some initial momentum. I don't know what it's going to be. Some big number. Your mass times the initial velocity, whatever that is. I'll call it, 7. Who knows? Whatever. It doesn't matter. It's just some number. 7,000. That's too big. P final's 0 though, right? Because you stop after you hit the wall. And so the issue here is delta T. Because the force, the average force applied is P divided by delta T. Change in momentum. Okay? So if your car is fairly rigid and barely buckles at all, delta T is going to be really, really small. And you are going to feel an incredible average force on your body. It's going to hurt quite a bit. On the other hand, if your car is the type... All right, so here's the wall. Here's the wall. If your car is the type of car to get real crumpled up, they crumple them in such a way that it doesn't kill the passengers. But if it crumples up, the collision happens over a long time. So the amount of time the collision takes is larger, and is smaller. So you feel less violent forces if you have more time to decelerate. It's monumental. All right, what's the last question? 3.91, 8.91. Yeah, this needed to be marketed to people because the deal is if you get in a head-on collision with something, or even a collision with the wall, if you're really heavy, like if you're in a huge, really heavy truck, and that collision is, well, whatever type of collision it is, if it's really big, because your mass is so large, the center of mass of the system, you and the wall or you and the other car, will be closer to your own velocity. And so after you collide, your final velocity won't be as far from its initial velocity as it could be. And the result is that your change in momentum isn't as big as it could be. So the deal was, if you drove a really heavy car, and your car was much heavier than the car you ran into, your change in momentum would be fairly small. And so the forces you feel would be fairly small. And so the chance of you surviving would be higher. On the other hand, the other person, not so much. If their car wasn't as heavy as yours, their momentum would change even more.